Boom. Okay, let's start things off. Any questions technically or logistically? A week from today we have our midterm, okay? The midterm will be held in here, although I am trying to get an auxiliary room to put a certain subset of students in, and we'll discuss that when I figure out exactly what I want to do on Thursday for planning. Okay, so some people may have to go to a slightly different room, but I assure you the tests will be the same. Any questions about that? Again, the midterm will be like about 5-ish problems, like the homework. Most of them are going to be from directly from exercises in the relevant chapters of the book. So some people have been asking me, how should they study? Some people have said, oh, should I watch the videos lots of times? And I'd say that's probably not the best use of your time. It's probably better than some of the other stuff that you watch. But that what I would recommend people do is they go through, work with their partner, go through homework problems, go through problems that are in the book, okay, as homework problems that we didn't assign. And for those, I want you to look at them, go through them, try to figure out what the idea is. Okay? Any questions? Okay? Any other questions about that? Yes? The midterm is, I believe, it is a week from today. Is that what everybody thinks? Yes. So I expect there's this lecture and one other lecture, and then we're going to go do it. Any questions? Okay. Put in the last problems of the day, and then I'm going to get going here. Okay. The problem of today is actually a very interesting one related to heaps. Put it in. Let's just go. No, that's not. Okay. The problem of the day is heaps, okay? And it has to do with heaps. And in particular, it has to do with searching in a heap, which is not really, or almost searching in a heap. Let's read exactly what it says. It says that we are given a heap on n elements, okay, and a real number x, okay? So we have this big heap which has a total of n elements, okay? N elements is in the thing. What's the height of the heap going to be? Log n. Okay, so this is log n in height. And we're given an element x, and we want to know, is the kth element in the heap, okay, greater than or equal to x? Okay, that's really what the question is. Okay, so the input is a heap, which we are given. We are given x, and we want to figure out, and k, and we want to figure out if the kth largest element is bigger than or equal to x. Okay? Kth smallest. So it's sort of the heap is, the smallest one is the root of the heap. We want to find if the kth smallest element in the heap is less than or equal to x. And we want to do that as efficiently as possible. Any questions about what the problem is before we go any further? Now, when I'm faced with a problem like this, I first ask myself, what is the straightforward way of trying this problem? It may be slow, but the correct, straightforward way of doing this. What would be the correct, straightforward way to try to tell if the kth largest element is there? Yes? So what you're saying is a heap is very good at extract min. That is what are the two things you do with a heap? You say find the min, which is the root element. That can be done in constant time. Deleting the largest element in the heap, okay, takes log n time, okay? You're saying go through and pull off the first k elements on the heap, okay? And then take a look. The kth element you pull off is the kth smallest in sorted order. Therefore, do the comparison. What is the running time of that algorithm? Okay, you've got different things. You've got here your n, you've got your log n, you've got your x, you've got your k. What is that going to be? Yes? K log n. Does everybody see that he's making k calls, each of which took log n time? Okay? You're saying k is constant. Okay, well, k is not actually tell you what if k is constant. Okay? K is k. If k was n, okay, if k happened to be as large as the heap was, it would be n log n algorithm. If k was 1, this would be an order n log n algorithm. You don't know what k is. K is part of the input, right? So the point is, this is a k log n algorithm. Does everybody see that this is an order k log n algorithm? Okay, any questions? So again, this is a useful hint in solving any of these problems. Before you try to get into the complicated thing, what is the brute force, straight, simple way of doing this? Okay? And as far as I can tell, this is the brute force, simple way of doing it. And it's not quite fast enough, but it is respectable. Any questions about that? Yes? How do I get k log n? How do I get any running time of an algorithm? The standard... All right, let me try this again. Hold on. Bum, bum, bum. Okay. Is that better? Okay. So the standard way of getting any of these running times, it's the number of things I'm doing by the time that it takes the biggest time it takes to do one, right? So what this algorithm is saying is, for I goes from 1 to k. That's really what it's doing. If you write this thing out, for I equals 1 to k, do extract min from the heap, right? That's y, and then the final question is x greater than y. This is the algorithm, okay? And it is a loop that is going around k times, each time doing an extract min, which is going to take log n in a heap. That is why it is k log n. How many people see why it's k log n? Any questions about that? Question like, I don't see why it's k log n is a good question. Any questions? Okay. Now, is there any other way we can think of to find out if the kth largest element in this heap is bigger or less than x? Yes?
There is an O of n way to do it, which is a linear scale.
So what is an O of n way to do it? Okay. There is an O of n way to do it. He's saying go through the entire heap, okay, and figure out one by one, look at every element, and say, find out which is the kth largest element on that scan. Okay? Now there's a little bit of detail here he isn't quite given, okay? Which is certainly in order n time he can look at every element in the heap. But how does he know which is the kth smallest one? Okay? He's got to have a data structure for that. Does everybody see this? Okay? It is not immediately obvious from the street level stuff that you know here. How are you going to figure out which is the kth smallest one? Do you agree with that?
Yes.
Okay. So one possibility is, what could he do? He could possibly, keep track of the kth smallest. How could he keep track of whether it's the kth smallest one? One possibility is he keeps track of the first k. Let's say maybe in sorted order. Okay? And then one by one inserts every new element that comes by, sees whether it's smaller than that, and if so, moves the thing over. That is sounding something like k times n. Okay? Or something like n times log k. Does everybody see this? Yes. Okay, so one thing that's saying here, so I think what you're trying to say is the following. What you would like to do is, actually, let me think, I'm trying to know exactly what you're doing. You want to know whether the kth smallest is less than this target. Okay, is that what you're saying? It has to do with this. Are you using the fact that you know what x is at first, or are you first just going to find what the kth smallest element in the heap is? Yeah. Yeah. Okay, I'm still not sure I'm completely understanding your idea, but it might be something like this. Okay, we've got a tree-shaped heap here, of course. And if I'm trying to figure out if an element is greater than the heap, if I have this element, if this element here is greater than x, what do I know about all of its descendants? They're also greater than x. Does everybody see that? Okay? So if I'm trying to find the elements that are less than x, once I have found an element that is greater than x, then none of its descendants matter. Is that sort of what you're saying or not really? Okay, so let's just go through the order n one more carefully then before we get any special here, just to see exactly how do we do it in a rigorous way. We agree that in order n time we can look at all the elements in the heap. We agree somehow we have to know what is the kth largest element in the heap. Okay? Now, how could we do that? Yes? Ah, okay, so this is an interesting idea here. Now what she's saying is, don't keep count, don't find the first k elements in the heap, right? Compare them to x and say, look at each one. If you are less than x, that's one guy that's less than x. I'm going to bop up my pointer. If you're greater than x, I'm not going to bop up my counter. If you're greater than x, I'm just going to move on to the next element. Does everybody see this? Now I am not maintaining a data structure here. All I am maintaining a counter is a counter C, the number that I see that are less than x. Okay? And that certainly, I believe, can be done in order n time. Okay? Does everybody agree with that? Now I have an order n algorithm, and I have an order k log n algorithm. Which is better? It depends, okay? If I give you k equals n, I tell you to find the biggest element in the heap. This is bad, and this is better, right? If I ask you to find the third largest element in the heap, or the fourth largest element in the heap, then this one is better. Does everybody see that? Okay? Any other ideas how we might find the kth largest element in the heap? Back there, yes. Okay, so now we've got another idea here, which says that the kth largest element can only be can't be, okay, below the kth level. Why is that? Because if we just take a look at any element on the kth level, there are k ancestors before it, all of which are bigger than it. Does everybody see that? So any element that is living deeper in the heap, okay, is going to have to be bigger than it. So we don't have to look at all n of these answers. We only have to look at the elements that are on the first k levels. Does everybody see that? What is the running time of that algorithm? Okay. What is it? Okay, not okay. Okay? Okay would be these elements. What is the running time? What about all the other elements in this region up here? Okay? Okay, it's 2 to the k. Does everybody see that? Yes. So this algorithm is order 2 to the k. Now let's look at these and decide which is better. Which is better, the order 2 to the k algorithm or the order n algorithm? Yeah? Order n? No. Which is the best one here? Order 2 to the k. Why? Because, order 2 to the k is a problem. What really is, if I say it's really order 2 to the k, then I'd be in trouble. But really what I think you were saying, although you didn't realize it, really was saying you were going to look not on all the first k levels. That's only if k was less than log n, right? If k was equal to 2 log n, you weren't going to try to find more levels of the heap than were actually there, right? So what you were really doing, it was order 2 to the min of k and log n. Does this make sense now? Okay, you can't probably read it there. That would be the min of k, 2 to the min of k, meaning all the elements on the kth level, and log n, because you were going to be smart enough never to look beyond the log nth level, correct? Even if I gave you k was equal to 2 log n, okay? So which is better? This is clearly always going to be less than or equal to n. 2 to the log n is n, right? So this one looks frightening. The 2 to the k min of k and log n algorithm is actually a smarter algorithm, right? It's smarter just to search the rows it might be on than to search all rows. How many people see that? Any questions about that? Okay. Any questions? Any questions? Like, I don't get that one. Yes, question. So I know that you know that the size of the heap is n. It's fair to say I'm telling you it's got n elements in it. Okay? So it's fair to say you know what n is, you know what k is, you know what x is. Okay? And now you want to look for it. Okay? Yes? Are heaps always linked lists? Heaps are presumably, in what we talked about before, not linked lists. Heaps are arrays. Okay? Embedded as an array. Okay? Any questions? So what we should be clear is we have several algorithms here that are interesting. This one is potentially interesting. This one is potentially interesting. This was interesting, but it's sort of subsumed by that one, right? The only thing that we don't have is one that runs in the time that we want it to run in, right? Any questions about that? Okay? Any other ideas? Okay, let me clear the screen and then let's say an idea. Let's say idea. Okay, so what he's saying recursively, he's sort of saying search the tree in a intelligent way, knowing what x is. Okay? Let's say what k is and what x is. Okay? Suppose, let's say, the root of our tree. We are looking to find the kth smallest element in the heap and how it compares to x. If the root of this is greater than x, what do we know the answer is? If the root of my heap was greater than x, okay, what's the answer here? Yeah?
Then the k small has to be greater than or equal to x because every element in the heap is greater than
okay, so that's right. So we have one element greater than x, right? If this element was less than x, what do we know? We have found one element that is less than x. And the only places where there are potentially other elements that are less than x are these guys, right? If we look at this node and find that it is greater than x, we want basically the question of whether the kth smallest element in the heap is less than or equal to x is really a question of whether there are k smaller elements than x. Does everybody see that? So let's count the number of elements that are less than x. Right? That was the idea. If we looked at the first k levels, that was the idea, right? But let's see if we can be cleverer and know when to stop looking. The moment we have an element here, if this element was greater than x, okay, then we know that nothing below it is worth searching. Does everybody see this? This guy is less than x. We'll look at this edge. If this was greater than x, we're going to stop. Well, now look at this element. Suppose this element is less than x. Well, then we're going to look at its children. If this element was greater than x, there's no reason to look below it. Does everybody see that? And by doing this exploration, one of two things is going to happen. We are going to visit k elements and see that they are less than x, okay? Or we are going to visit less than k elements and find that all our paths to elements less than x have been shut off. Does everybody see that? How many people see the idea that I have? Okay, any questions? How many people don't see it and want me to try and explain it again? Okay, nobody. Okay, what's the running time of this? Okay, note that it is a tree. The number of internal nodes in this tree, the ones that are less than or equal to x, that we're going to be interested in, there's going to be at most k of them. Because once we've found k ones that are less than x, we give up. We have our answer, right? And the number of mistaken ones that are bigger than it would correspond to leaf nodes on the tree defined by that, of which there are no more than twice as many of them. Does everybody see that? Okay? Because in a tree, the number of internal nodes, if you have a binary tree, here I've got 2 internal nodes, I've got 3 leaves. Okay? The number of dead-end leaves that I'm not going to visit beyond is going to be at most essentially the number of internal nodes. So if there are k internal nodes, there are k or 2k external nodes, we're only going to look at order k nodes. Okay? And so this procedure is order k. Okay? How many people believe the search procedure? How many people understand the analysis or have a question about the analysis? Okay, understand the analysis. How many people have a question that want me to go through the analysis again? Yes. Why is it order k? Okay? So the way that I like to why is the running time order k? Or is that... Okay, so how do I count running times? My simple way of counting running times that works most of the time is I count how many things do I do times how much does it cost to do one of those things. Looking at a node, how much time does it take to look at a cell in my heap and decide if it is less than or equal to x? How much time does that take? One step, order 1 time. Now I'm going to explore elements in this kind of traversal manner. Okay? I'm going to explore at most k elements that are less than or equal to x. Okay? And I'm going to explore at most 2x elements, okay, that are bigger than or equal to x. Okay? 2k elements that are bigger than x. I think it might be k minus 1, but I like to round up because I'm big O thing. Right? And so therefore I am doing something like 2k or 3k things, each of which took order 1 time. K times 1 is k. That is why it is order k. Any questions? Yes? You're saying it's a pre-order traversal of this heap. Well, first of all, it's not really I'm not sure I'm going to call it a pre-order traversal of the heap. Because pre-order, as you think of it, applies to binary search trees. Right? It has to do with the labeling. Okay? But you're right in saying that what I'm going to do is look at a node, decide if it's worth exploring the children. If it's worth exploring the children, I'm going to call myself recursively on the children. Right? And if not, keep going. Right? What does this algorithm look like if I code it up? Let's look at this and see if we can come up with a pseudocode-like representation of this, because maybe that'll make it a little clearer. What is the idea here? Suppose, let's say out here, I start out with a thing where I say count equals 0. Okay? And so I know these are the number of elements I know that are less than x. Right? Let's say I'm going to call my search procedure where I'm given a node in my heap. Let's call this thing I. I'm at position I in my heap, and I'm looking for element x. What am I going to do? I'm going to say if, basically the array element sub I is, I guess, less than x, then that means I want to add it to my count of the lower ones, right? So what am I going to do? I'm going to do count equals count plus 1, right? And now I know that this element is interesting. Okay, I am going to go do what? I'm going to now do a search. My left child. Where is my left child? Where is the left child of node I in the heap? 2i for x. And I'm also going to search my right child. A sub 2i plus 1 sub x. Okay, see how this is recursive like? And there's one thing I forgot, which is to say, if count is greater than x, if count is greater than k, return. Okay? So what am I going to do? If I have already found enough elements that I'm not interested in finding any more elements less than x, I return, right? If not, I'm looking. My looking means go to an element, increase my count, okay, and do my search. I guess I could probably move this search thing in here, my condition test in here. But who's counting? Okay, one way or another. The important point is I'm searching any element that matters. I quit whenever I have an element, my count is greater than it. That's the important point. Okay? And now I'm only going to be searching at most k live nodes and at most something like k or 2k ones that end up failing this test. If it fails this test, I don't let my else's do nothing, just bomb out of my recursive call. Okay? Any questions? How many people here see that this recursive code is computing the right thing or something like the right thing? How many people don't see it and want me to explain it again? Okay, a couple of people. Good. What is basically my procedure going to be? I start at the root, right? Is this element less than or equal to the value x? If it is greater than the element x, I bomb out and do nothing, right? If it is less than the element x, I increase my count of the number of elements less than x by 1 because I have seen one. And I start to recursively explore this side and then potentially this side. Because the children of this are also potentially less than x, right? I start recursively working on this side. Is this element less than x? Turns out the answer is no. So under that condition, I bomb out of the recursion, come back here. I then execute the second clause here on this side. Is this element less than x? The answer turns out to be yes. So I found another one, and I explore this side. I explore this side. I explore this side. The moment I have found k elements that are less than x, then I'm going to return. If I stop before that, I will have had less than k internal nodes. Okay, the number of places that were greater than x are going to be my leaves. There's at most k-ish of those. So k plus k-ish is k. Okay? And each one of these things took constant time. Yes? K is part of the input. Okay? So if you look at this thing, k is, I'm assuming here, is a global variable. That's a good question. But k was part of my input, right? The question here was, find out if x was greater than or equal to the kth smallest element, right? So that's why I had this here. I had a global variable here where I had k so I could test it within this subroutine, right? No, we don't want to find out what the number of k is. We want to find out, let's look at the original problem. Let's go back one more time, look at the problem. Kabunk, back. Your algorithm should determine whether the kth smallest element is greater than or equal to it. That is a true-false question. Any questions? Okay, does everybody see that this algorithm solves this question and how you reason about it? Yes? I find k smaller elements less than x. Yes. Basically, I'm not creating this tree. When you give me a heap, right, you're given a heap. That heap is an array-based heap. Implicitly, that is a binary tree, right? It's got every node has a parent, every node has 2 children, okay? So it is a binary tree, and so I can now work on it and analyze it like that. It's not a binary search tree. It's a binary tree. Yes?
So is the worst case scenario going to be you have to search k on each side so that you can get it?
The worst case scenario would be, I think, that I come to a world where I have got exactly k minus 1 yeses. How many? To be precise, I've got k minus 1 elements that are less than x, right? And everybody else, okay, is no, right? This is, I think, my worst case, right? At the point where I've got, in this case, 1, 2, 3, 4, I think I've got k no's and k minus 1 yeses, right? It's like I got a full count now. Let's say I didn't have this one here. I've got k minus 1 no's, k minus 1 yeses. I've got one element left to explore. If it is a no, it will have shut me off, and there can't be anything else less than that. If it's a yes, it means I have found a kth one smaller than it. Does everybody see that this is the worst case is when I have as many no's as possible and as many yeses as possible? Okay, it's like a full count in baseball. It's 3 balls and 2 strikes. Okay? The next pitch, something's going to happen. Okay? And that is the worst case here. Any questions? Yes? Okay, so you're saying the worst case is not okay. The answer is this is the worst case. Because suppose my tree is huge. It's got n nodes. It's a Himalayan tree. It's heap. It goes back millions of nodes in it, right? I am going to stop if k is the input. Okay? If k is less than n, I am going to stop after looking at 2 times k nodes, even if the tree had a million times k nodes in it. Okay? I am only going to look at order k nodes in the tree, regardless of how big the tree is. Okay? Because I'm going to stop myself once I have found too many that are smaller. And if I don't find too many that are smaller, it's because I have found enough that are bigger that block off the possibilities. Okay? I'm not going to be searching at the descendant of any node that has already been too big for me. And that's why I'm only going to search order k nodes. Any last questions here? Think about it. Yes? What if I want to find the kth smallest element instead of the actual one of these? Right? Okay. Instead of comparing it. So now that's a harder question. Here, the k log n algorithm looks pretty good, actually. If I actually want to find the kth smallest element, the k log n algorithm is probably about as well as you can do for small k. Okay? Any questions? Now note that for big K, that's actually, for big K, it sort of becomes something like median finding. What's the median? The median is the n over second largest element in there, right? Remember we talked about finding the median? My daughter, knew what the median was? The median was the element where there were n over 2 elements bigger and n over 2 elements smaller, right? Finding the kth largest element is a lot like finding the median. Does everybody agree with that? It's the median for k equals n over 2. The problems are the same. So similar techniques for finding the median are the right way for solving that kind of thing. Okay, and it turns out in this case it's pretty much going to be based on what you know. Let's say I like the k log n solution based on what you know. Okay, any questions here? Okay, fair enough. Any other questions about heaps or finding things in heaps? Okay, good. Okay, what I'd like to talk about now are two other sorting approaches, one of which I'm going to give a very quick shift through because I want to spend more time on Quicksort than Mergesort. Just because that actually in some sense has a bigger lesson at the end of it. What is Mergesort? Mergesort is a representative of a class of algorithms which are worth knowing about called divide and conquer algorithms. What are divide and conquer algorithms? They're based on the idea that you take your problem, you divide it into two pieces, you solve each problem, and you have a way of combining the answers from those problems in a way that it takes less time to combine the answers to each piece than it does to solve the pieces individually. Okay? And so for sorting, Mergesort is based on the idea that if I am given a lot of elements to sort, I will break the thing arbitrarily in half. If I have n elements to sort, I will first sort all of these elements in decreasing order. I take my second half of the elements. I sort them. They're going to be in decreasing order. Okay? Now I have n over 2 elements here and n over 2 elements here. Both are sorted. The claim is that I can, given that they're sorted, merge them in order n time by just looking at it. If I have two sorted lists, where is the smallest element? Suppose I give you two sorted lists of numbers. Here is one list, here is the other. Each list has a head, each list has a tail, right? If I ask which is going to be first in sorted order overall, where is the first element in sorted order overall? Somebody knew, okay? Where is the element that's going to be first in sorted order if I have done this? Anybody? Somebody else? You answered too many questions. Somebody else? Okay? Somebody. Help me. Okay, yes. Oh. Does everybody see that the first element in the list has to be either here or here? If I want to figure out who is the smartest person in this class, and I have the men in the class sorted by brains, and I have the women in the class, and they're sorted by brains, who is the smartest person in the class? It is one of the people that is at the head of one of the two people at the head of their respective lists, right? I compare them. Which one of them is smarter? Pull that person off. They're smartest overall. In one step, I've identified who is the first guy, okay, and reduced my problem by 1 in size. I am now again going to compare which is bigger, the head of this list or the head of this list. Whichever one is smaller, that's the head of it. I'm going to put that guy over here and move down. There are n over 2 elements here, n over 2 elements here, a total of n elements. In one step per element, will have combined those lists, merged them into one sorted list. So the beauty here is that once I have this half sorted and this half sorted, the merging step is order n. Any questions about that? I may say that again in a couple of slides, but we'll just go through it now. Kabunk. So here is the recursive implementation of Mergesort. Okay? It is recursive. It says to sort the elements in an array from low to high. What am I going to do? I'm going to compute the middlest element. I am recursive. So if this is an array, big array, I'm now asked to sort the elements from low to high. I find the mid-range between them. That's just finding the average. Sort the left, sort the right, and then basically merge these elements into one sorted thing. This is a recursive call. The other is calling an auxiliary routine that, given two subarrays, merges these subarrays and writes them back into that same location. Any questions about that? Okay. bunk. Again, that's a picture of it, but I think I like my picture better. Okay, so what is the running time of this thing? Again, the important point is that the efficiency is going to depend upon how fast we can merge the two halves into sorted lists, okay? And again, I said that basically by constantly pulling off the smallest element, if each list is sorted, I've got two heads at all times, pull the smallest off, compare the remaining two heads, pull the smallest off, compare the remaining two heads, pull the smallest off. In a total of n minus 1 comparisons or n total work, I could merge two sorted lists, each of which have a total of n elements. Any questions about that? Now, what is the running time of the entire algorithm? Okay? Again, first of all, one question here. There's a little thing. If I have this thing stuck in an array, and I have the sorted list 4, 5, 6, and the sorted list 1, 2, 3 here, merging them, if I do it in a naive way, without using auxiliary space, is going to be a problem, because the min of the head of this and the head of this belongs in this position. I'm naturally going to want to write it there and erase that element. Does everybody get that idea? So what is the right way to do it? Malloc another array. We're only living in big O world, right? Malloc another array and copy the elements when you merge them into here. Does everybody see that? Then I can just copy back these elements into my array, and the total time is obviously order n, or linear in the size of the array. Any questions about it? So in fact, there's a little bit of dealing with buffers here, but it doesn't cost us anything in a big O sense. Any questions? The interesting thing about the interesting thing about merge sort is understanding why it is going to be order n log n. Why is it going to be n log n? Okay? It has to do with the fact that let's think about it like a recursion tree. Maybe this is what I would like to do. Originally, to sort all n elements, how did you solve that problem? You solved it by breaking it into two arrays, each of which were of size n over 2. Does everybody see that? Because you put the middle element. And when you recursively sorted this, you broke this one into two halves. Okay? Each piece of which, that one there, this one here, each piece of here of which was n over 4. Does everybody see that? This piece of n over 4, when you divided it, became two pieces, each of which were n over 8. How many levels deep did the recursion go before we stopped? Yes? Log n. And why is it log n? It's how many times do I take n and divide it by 2 until it gets down to 1. How hard is it to solve a sorting problem on one element? If I have an array of size 1, how do I sort it? I just walk away. It's sorted, right? Does everybody agree? It's done when I've got one element. Okay? So what is the argument? If I think about what's happening with merge sort, I am basically getting a perfectly balanced binary tree of height log n. Now, how much work is being done at each level? This is where you have to think and listen to me for a minute. In going from this level back to here, when I had the two sorted half arrays, how many steps were being done? This was n over 2 elements that had already been sorted. These are n over 2 elements that had already been sorted. Merging them took how many steps? Yeah? N. So this was n steps. Now let's look over here. Suppose this was sorted and this was sorted. This had how many elements? This had n over 4 elements in it, and this had n over 4 elements in it, right? And when this got merged and merged, how much time did it take Wait, actually, okay, wait, my picture's a little bit wrong. Here I have, let's look at this element to be precise, okay? This was n over, this is n over 4 elements, right? This is n over 4 elements. This is n over 4 elements and n over 4 elements. Does everybody agree with that? To create this thing, let's maybe redraw it over here because my picture's now a little crummy. To create that thing was the result of merging this piece, which was n over 8 elements, with n over 8 elements. How much work did it take to take this sorted thing of n over 8 elements and this sorted thing of n over 8 elements and merge it into n over 4 elements? How many steps did that take? Say about n over 8. The answer is not n over 8. Okay, it's because n over 8 is how many elements it took just to compare against these. I eventually am going to be, in each round I'm doing one comparison to create one of those. It's going to be n over 4 comparisons. Okay? How many people see why it's n over 4? Okay, if you see why it's n over 4, then we're in business. Because if it's n over 4 steps to produce this, and n over 4 steps to produce this, and n over 4 steps to produce that, and n over 4 steps to produce that, 4 times n over 4 is what? N. This is the same pattern that we're going to have on the next level. The next level we're going to have n over 8 runs, each of which took n over, and have 8 runs, each of which took n over 8 time to make. If you work through that, that is a total of n steps per level. N steps per level times log n steps. Levels is n log n. Okay? Any questions about that? Question like, say that again is a good question. Any questions? Draw it again. I couldn't read your slides. That's a good question. Any questions? Yeah? Say that again. Okay? So what am I saying here? Let's look at my, maybe I'll even go to the here to make to go to here and explain it on a bigger board. Okay? That may be the problem. Okay? So let's think what is happening in the course of a merge sort. Okay? The recursive call does essentially nothing, right? It finds what is, if this is, you say call it sort an array from 1 to n. It does nothing but compute what n over 2 is, right? That's a constant step, right? And then it recursively called itself on this chunk, okay? But calling itself on this chunk meant calling itself recursively on half of that piece. On this side, it was half that piece. On this side, this was going to be half that piece. This side was going to be half that piece. This side was going to be half that piece. This side was going to be half that piece. Okay? Now, what are we doing? At the bottom level, when this element got to be 1 element each, okay, it's not doing anything, right? Because everything is already sorted. The real question is what happens in the merging, okay? And so let's count the cost of the merging. We have a total of log n levels. In this case, what are we doing? To create this element, we merged something that had n over 2 elements in sorted order with n over 2 elements in sorted order. That took exactly n steps. Does everybody agree that that part of the work took n steps? Let's now look over here. What was involved in creating this? This has n over 2 elements. It was made by 2 things, each of which had n over 4 elements, right? How much time did it take to merge something that had n over 4 elements plus something that had n over 4 elements? How many merge steps were involved? How many comparisons? N over 2. Because it's linear in the number of elements that I have, right? So it's n over 2 steps to make this, and similarly, n over 2 steps to make that, right? What is n over 2 plus n over 2? What is that? n, good. If you were teaching in this class, if you listened hard enough all semester, I've said it's equal to n over 2, right? Big O-wise. But we're not dealing big O. We're counting exactly here, right? What about on the next level? To make this piece of size n over 4, I had to do what? Here was a piece of size n over 8 and a piece of n over 8. How many steps did it take to produce this piece? N over 8 plus n over 8, right? Which is? N over 8 plus n over 8 is? N over 4. So that was n over 4 to make this, plus n over 4 to make this. What is n over 4 plus n over 4 plus n over 4 plus n over 4? What is that? N. Does everybody see that there's a, because we break this thing up and we're doing a linear amount of work on each piece, one of the nice things about doing a linear amount of work in a piece is that any way that you break up n into pieces and sum it up, it's going to be order n. Okay? And what this is saying here is that there are log n levels. When you view the computation like this, there are log n levels, each of which takes order n time. N times log n is n log n. And that is the reasoning why merge sort is n log n. Any questions about? How many people get it? How many people don't get it? Any questions? Any questions like why merge sort is n log n? Okay? The key step in here is that I am doing a linear amount of work per level, and the tree is perfectly balanced. So there are only log n levels. That is the thing that makes merge sort go. Any questions? Okay? Going once, twice, sold. Okay? So that is heap merge sort. We're going to see a lot of n log n algorithms. Why is it that anybody cares about merge sort? Well, you know, in some sense, from our point of view, big O-wise, it's no different than heap sort or anything else. They're both n log n algorithms. In the way I normally think of things, they look the same. In fact, if you use, however, it turns out that merge sort turns out to be very good if you are sorting things on disks, okay? That, you know, sorting, when you're really sorting big files, okay? Like you want your Facebook and you want to sort everybody who has a Facebook account from first in alphabetical order to last in alphabetical order. Even Mark Zuckerberg does not have a computer big enough to store everybody's Facebook name, okay? To sort in main memory. The way that thing is going to have to happen is it's going to have to be a computation that happens on disks, okay? And it turns out that because of the behavior of how you access data in this case, you sweep along the sorted files, you get to exploit some of the good properties of disks if you do this merging step that you don't get when you're randomly jumping around the file. So that is one reason in practice why we care about merge sort, okay? But the bigger thing is it provides another way to think about an n log n algorithm. And in particular, it provides a good example of something we call a divide and conquer algorithm. What is a divide and conquer algorithm? It is basically a way that we solve a problem by breaking the problem into two halves, okay? Solving it on each half, okay? Or figuring out which half we have to worry about, okay? And if something is easier to solve, you can break it into smaller problems, each of which you can solve recursively, and then merge the answers efficiently into a solution, okay? That is what the idea is behind divide and conquer, okay? It's what we do with binary search. How does binary search work? We take the problem, divide it in half, and in constant time throw away half the problem. That is a divide and conquer algorithm. In merge sort, we take it, we divide it in half, solve each of the pieces, and combine the results in less time than it took to find the pieces. If you have that property, you come up with efficient algorithms. Okay? And there are a bunch of algorithms that are well known and famous, okay, that we're not going to discuss in this class, that are based on divide and conquer. It's an important idea. Okay, if you know about Fourier transforms, the FFT is solved by a divide and conquer algorithm. If you don't worry about it. You know about matrix multiplication. I talked about matrix multiplication earlier. I told you, we showed that the standard way you learned in school was order n cubed. If you have multiplying two matrices that are n by n. In fact, there's a super fancy, complicated order n to the something like 2.37 algorithm based on divide and conquer. Okay, I'm not going to go through it, but just a proof that this idea of dividing it into pieces, solving the pieces and putting them back together in the right hands has power. Okay, and so it's something you should be aware of. Any questions about divide and conquer? Any questions about merge sort? Okay. At this point, I'd like us to clear our heads a little bit and talk about the other sorting algorithm of the day, which is Quicksort, which I'm pretty sure most people have heard of. Who has been presented Quicksort before? Raise your hand. Who has never seen Quicksort before? Don't be shy. Okay? So Quicksort is yet another sorting algorithm that in practice has the property that for stuff that is going to be kept in main memory, it is arguably the best of the n log n algorithms. Okay? But it is not actually best in worst case. And what makes Quicksort interesting is we're going to see it's an example of a very important paradigm of algorithms called randomized algorithms. Okay? And that is why when you're saying, oh, why is he going to explain Quicksort again? The reason is I want you to really understand the idea of how randomization helps you solve problems that otherwise don't seem like they could be solved so easily or efficiently. Okay? And so that's what the big idea here is. Okay? But let's go through what Quicksort is before we can get to the big idea for where the randomization comes in. Okay? Quicksort works as an algorithm that works using an idea of partitioning as its main idea. We are given as input an array that is unsorted. It's got n elements in it. We're going to pick one element. Okay, let's say the last element. Okay, and say that is going to be my pivot. What my pivot is my partitioning step is, I'm going to take a look and figure out for all the elements in the array, the ones that are less than this pivot, I'm going to put to the left. The ones that are greater than the pivot, I am going to put right. And the pivot element, I am going to put in its proper spot. Okay? So let me go through and see how can I do this. How can I take my pivot element, in one sweep through the array, figure out, put elements so that, partition the elements, so that all the guys that are less than it go to the left of it. All the guys to the right of it go to the right, that are bigger than it go to the right of it. And the pivot itself ends up in the right spot. Okay? How can I do this? My basic step is going to be as follows. I'm going to keep track of a pointer to all the elements that are less than the pivot. This is, I guess, less than the pivot. All the elements I know that are greater than the pivot, and everything else that's in between. Okay? So what am I going to do? Suppose the first element in my array is less than the pivot. Let's say my pivot was 10, and the first element was 5. How could I adjust things in constant time so I still know what's to the less than the pivot, what's greater than the pivot? Yeah? Well, swap them. I don't want to swap anything yet. If this element is less than the pivot, all I want to do is to move my less than the pivot bound over by something. Does that make sense? Okay, if this guy is 1, it's less than the pivot. Okay? That's fine. I can move my pivot less than the pivot pointer element over, right? But what if I come up with an element that is greater than the pivot? What can I do to keep my bounds? Okay, I can swap them. Okay? What if I swap 13 with whatever happens to be the last guy next to my greater than pivot pointer? What's going to happen? This guy is going to come over here. 13 is going to go over there. The less than the pivot pointer moves over, right? And now, after one more step, I have maintained my invariant, that all the elements less than the pivot are, all the elements less than this index are less than the pivot. All the elements in positions greater than this index are greater than the pivot. Okay? If I do this in one step per iteration, okay, I will, after n steps, have put everybody, I'll know everybody's, here the guys are all less than the pivot, here the guys are greater than the pivot. Now I can copy my pivot back, and it's in the right spot. How many people get that strategy? Okay, any questions about that? Do people see how I can do this partitioning in time that is order n? Okay, that's the key step here. You pick a pivot, okay? In order n time, I can segregate my elements into those that are less than the pivot and those that are greater than the pivot. Okay? Any questions about that? Okay, if you look, I think I have an implementation of that here. So if you're telling me, again, this is basically the idea. In one linear scan, I'm going to maintain 3 sections of my array, less than the pivot, greater than the pivot, and unexplored. I'm either, as I scan from left to right, I either move the left bound to the right, or I swap it with the rightmost unexplored element and move the right bound to the left. N steps like this, I have finished my partition. Okay? And so one of these partitioning steps takes order n time. Any questions? Now, what progress? Suppose I have partitioned an array. So here I've got it. Here's my pivot P. Okay, and these guys are less than the pivot. These guys are greater than the pivot. What good? I have spent order n time, okay, to get to this state. Why is this state help me? Is this better from a sorted point of view? Okay? After I've done my partitioning, have I made progress in sorting it? Okay? I claim I have made progress. I've made progress in 2 distinct ways. First thing I'd like to claim is that the pivot element is now in the element spot that it's going to sit in final sorted order. Why must the pivot element be, the pivot element after I've done my partitioning might be in the 176th slot? How do I know that that element is going to be in 176th position in total sorted order? Yes? Right, right. If you're saying, hey, I'm ranked 196th in the Stony Brook graduating class, why are you ranked 196th? It's because there are exactly 195 people who are better than you, right? Those are the ones that are less than you. The pivot, by definition, has taken, partitioning has taken anybody that is less than the pivot and put it over in that group, okay? So the pivot is in the right spot, okay? Any questions about that? That's got to be clear. If that's not clear, then the correctness of the algorithm is in question. Any questions? The other thing to note is that after we've done the pivoting in sorted order, in the act of finishing the sorting, these elements are going to jumble around, and these elements are going to jumble around. But there is never, never, never going to be an element from this side that belongs on that side. Why is that? Why do we know that in the course of sorting, no element that was put on this side of the pivot is going to sometime flop to the other side of the pivot? Okay? Why? Our invariant is, in order to have gotten into this club, you had to be bigger than the pivot. In order to be to the left of the pivot, you got to be less than the pivot. You can't have it both ways, right? So what's great here is no element's going to flop after that. And therefore, we have broken our sorting problem. Now we can independently sort this half and independently sort half that half, or not half, this part, and then sort this part. And once they're in the proper places, the entire thing is sorted. Okay? Any questions? So this idea gives us another recursive algorithm that looks, in some ways, when you look at the program, sort of like merge sort in many ways. It is a recursive algorithm, right? Okay? Basically, it's going to partition the elements, okay? I guess in merge sort, we didn't quite do the same thing, but we sort of split them equally in half. Here we found a pivot element somehow and partitioned the elements around the pivot. Then we told where did the pivot end. Then we're going to quick sort the left part of the thing, the stuff from the beginning of our array to just before that pivot, and just after the pivot to the rest of the array. Okay? This is going to again be a thing where we're going to spend order n time, okay, and have two recursive calls on smaller subparts. So this should smell and look a lot like merge sort. What did merge sort do? It broke the thing into two equally sized pieces, okay, and then recursively sorted each half, okay, and did a total of n extra work. What is the difference here between this and merge sort? Yes? I randomly select my pivot point, which means what? Yeah? What's the impact of that? Yes? It is not necessarily divided equally. That is the big difference here. Okay? So let's now look at the analysis of this thing. What is the best case of quicksort? The best case of quicksort, again, there's various pictures here, is going to be exactly like it was sort of with merge sort. That when we picked our pivot element, we happened to get extremely lucky. And every time we picked our pivot element, it happened to be the median of the array. If so, then n over 2 elements ended up to the left, n over 2 elements ended up to the right, recursively solving this thing. If every time our pivot was the median, then we would have a tree that was how tall? How tall would our tree be? Log n. How much work are we doing? Well, the time it takes over here to partition this is linear in the number of elements. 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 The sum of these pieces is the number of comparisons we're going to do, and that is always less than or equal to n. Okay? So we have, if it's perfectly balanced, we have log n levels. And at each level, we're doing a total of at most n work. N times log n is n log n. That is why quicksort is n log n if we do it perfectly. Any questions? What, however, is the bad case of quicksort? Okay? What if we were unlucky? Let's say clear ink. Kabunk. What happens if we are very, very lucky in picking our pivot elements? Okay? Suppose the pivot element happens to be, we look and we happen to pick the min element as the pivot. Then nothing goes to the left. The pivot element ends up in the first spot, and we've got n minus 1 elements, and n minus 1 elements in this chunk instead of half of them. Let's say we get unlucky again and pull off the first one. Let's say we get unlucky in a different way next time, and we pull off the biggest element in the remaining array. Then we're going to pull this element off, but still we've got a big chunk. Does everybody see that? So what is the height of this tree going to be? n minus 1 if we want to be exact. But if we split off one element each, you've got something where the height of the tree is going to be about n. Okay? And the cost of pivoting this is going to be n steps. The cost of pivoting this is going to be n minus 1 steps, n minus 2 steps, n minus 3 steps. What is the sum as it goes from 1 to n minus 1? Okay? On average, the average one of these things is going to be of size n over 2, right? And so we're going to spend on average about n over 2 comparisons, okay, n times. This is going to be an n squared algorithm. How many people get that? Any questions? Any questions why Quicksort is n squared? The real interesting thing, okay, is why is Quicksort usually good? Okay? And this I want to give you some kind of an intuition. Suppose you pick the pivot element at random, okay, where instead of, let's say, being always unlucky, you're just going to draw the elements, you're going to pick an element uniformly at random. Now, in sorted order, let's say we put the elements in sorted order. The elements in the gray are the elements that rank from n over 4 to element 3 over 4 in sorted order. They're in the middle of the sorted order, right? This is the top of the graduating class. This is the lucky to graduate part. This is the median part, right? How many people are in the middle of the class? Okay, and as I look at this thing, how many people are in the middle of this class of size n? Yeah? n over 2. Now suppose I randomly close my eyes and I pick one of you here. What's the probability that you are in the middle of the graduating class? Okay? It is going to be what? 1/2. Does everybody see that? 1/2 the time I'm going to pick somebody from the middle of the graduating class. Okay? If I do this 10 times, I am likely to come up with about 5 people from the middle. Right? Does everybody see this? If I'm really picking randomly with my eyes closed, the probability I end up getting a middle guy is 1/2. Right? Does everybody see that? And see, this doesn't depend upon, if I'm picking them at random, it doesn't depend upon how lucky I am. I mean, it doesn't depend upon, it depends basically upon me being lucky. It doesn't depend on what the elements actually are. You guys may all be great students, or you may all be lousy students. If I randomly pick one of you, there's a 1/2 chance I'm going to get one of them you guys that are in the middle half of quality. Okay? Any questions? Now note that here, unlike at grade averages, the middle half of the class is actually the ones that make the best pivots, right? These may make the best programmers, but these make the best pivots, right? Because if I pick any one of these n over 2 elements, okay, I am going to get somebody where the biggest hunk of the array, okay, is at most 3n over 4. Does everybody see that? If I pick the worst possible good pivot, okay, then this is what I've got. Does everybody see that? The worst possible good pivot still will divide off a constant fraction of this thing. That's the important thing here. Okay? Any questions about that? Let me keep going. So let's say I always pick the worst possible good pivot. Okay? What would my tree look like if I always picked the worst possible good pivot? At first, the whole array would be of size n. What would be the biggest piece the second time around? How big would it be? 3/4 n. Right? Suppose I do it again. What's the biggest piece going to be the second time? 3/4 of 3/4 n. Does everybody see that? Or 9/16 n. In general, if we go through this, I just like this very intensely. So, kabunk, kabunk, kabunk. In general, if each time I divide it by 3/4, how many levels, if I start out with n elements and I keep multiplying it by 3/4, how many times will I multiply it by 3/4 till I get down to 1? It's n times 3/4 to the L equal to 1. That's another way of writing that, is just simply to put it on the other side. It's n equals 4/3 to the L. This is really saying that basically L is going to be the log base 4/3 of n. Does everybody see this? If I always pick the worst possible good pivot, I'm going to end up with a tree that is of logarithmic height. Does everybody see that? How many people see this? This is important, okay? How many people don't see this? The log is not base 2, but does the base of the log matter big O-wise? No, it does not, okay? So I've got a tree that if I think about just making, if always you guarantee me the worst possible pivot that's good, the height is going to be log n. Now, in practice, is every one of my pivots going to be a good pivot? No. What fraction of the pivots are going to be good? Half. How many of them are not going to be good? Half. Suppose I always pick the worst possible not good pivot. Half the times you agree I will pick a good pivot, and half the times I will pick a bad pivot. Suppose I always pick the worst possible of each type. That seems as unlucky as I can fare to get, right? When I pick a bad pivot, I get essentially no partitioning, right? But what is the pattern of pivots going to be as I move down the tree? Is it going to be likely going to be bad pivot, bad pivot, bad pivot, bad pivot? No, because roughly half the time it's going to be a good pivot. Does everybody see that? So what does that mean? On any path through this tree, to get to a leaf node, I will probably have an equal number of good pivots and bad pivots. And the number of good pivots I can have can't be more than log n, or 2 log n, something like that, right? Log base 4/3 of n is how many good pivots I can have on any path. The number of bad pivots is going to be equal to the number of good pivots, meaning the tree of both good and bad pivots is going to be at most twice the height of the number of good pivots, on average, expecting it, okay? And that is the intuition. Why, that is the intuition. Why the height is going to be log n, okay? Didn't quite say the punchline clearly enough, but I want to see if you guys understand it, okay? Does everybody agree that my root, it could be a good pivot or a bad pivot, and there's a 50-50 chance of each? Its child can be a good pivot or a bad pivot. There's a 50-50 chance of each. It's going to keep going down until, okay, it gets to a region of size 1, at which point that's done, right? How many good pivots will we have encountered in going from the full array of size n down to 1 along any path? We can't encounter more than log base 4/3 of n. Because each time we divide it by 3/4, we can't divide it by 3/4 more than that many times. How many people see that? Okay, nobody. Okay? Any questions about it? Okay? The argument here is I can't have that many good pivots. And I'm going to have as many bad pivots as I have good pivots. So I can't have that many total. Okay? The height of the tree is going to be order log n, because it's definitely going to be log n, at most log n good pivots on any path. And the number of bad pivots is going to equal the number of good pivots on that path. Any questions about it? I want people, don't move yet. Give me a minute or two just to make sure we understand this. Any questions about why it is log n on average? Okay? Any questions about how many people see it or feel it? Very few people are feeling it. How many people have a question? Again, I want you to think about this, because if you take a look at it, there's a more formal way to do this. Okay? I could give you an argument about solving a recurrence relation and then show you the math involved in solving this recurrence relation. And if you think this is a better argument as to why it is n log n, you're happy to read it. But I want you to understand the intuition. The intuition is that good things are likely to happen with every pivot we take. It is hard to pick pivots that bad things will always happen to it. In this case, the odds are stacked in our favor that we will make progress with each pivot, okay? And that is why it expects to be n log n. Thanks for your attention. We'll talk a little bit more next class about it and then move on. Yes.